Good morning, good afternoon. My name is Mohammed, and today I'll be delivering on the topic a delta C detection circuit for capacitive sensing based prosthetic control. Okay, these are the outlines that we'll try to go through. First, we'll see the present technology or the existing technology for the prosthetic control and what limitations do they pose. Then we will see how can we use capacitive sensing to for eliminating these drawbacks. Then we'll see the workflow in which we have developed the bionic hand. It's an ongoing work. Then we'll see the interfacing circuit that we have proposed, and finally we'll go through the results. Fine. So every year almost 30 million people have to go under limb amputations. Fine. For different causes. It may be through due to an accident. It may be due to some kind of disease, for example due to a diabetic wound. Fine. It may be due to cancer, anything. Fine. Now such persons, what happens with them naturally, they lose somewhat of their mobility. Now to increase or to bring that mobility, what do? We use an artificial prosthetic hand. It is not up to the natural mark, obviously. So what do? We use a prosthetic hand which is artificial in nature. Currently, what we use electrical signals from the muscles to control these prosthetics for gesture control, holding things, but there lies an issue with this. Fine. What is the issue? Currently we are using EMG or electromyography for controlling of these prosthetic hands or bionic hands. See, surface EMG, what do? We take some sensors, we place this on our arms or wherever the limb has been amputated. Fine. Now let us suppose a person is supposed to wear this for 24 hours. After 24 hours, his arm will be all swollen up due to these electrodes. There will be rashes, there will be irritation. So you see there is an issue. Fine. This is a smaller issue. Medical people might be knowing better. But from the engineering point of view, what the issue seems to be, it has very poor spatial resolution. Very poor spatial resolution. What do we mean by that? There is not much smaller activity that can be picked up by these sensors because there are large impedance mismatches, even through the gels and all. Fine. Then what people did, instead of surface mounted EMGs, what they did, they used implantable EMGs. So basically they do a surgery and put the electrodes inside, but it also has an issue. Although the spatial resolution is much better, it works much better, but it results in permanent damage. Fine. Now a person who has already gone under a limb amputation, after 3 months you are telling him to go under another surgery. So imagine what he goes through. Okay. And there also when an electrode is buried inside you in a muscle, the rate of infection or the chance of infection is much higher. So people used EITs. Fine. In EITs they check the conductivity and the permittivity of the skin or the muscles, but these are not really portable because you have to first inject a current into the skin itself. Fine. Then Einers have been used. These are light based. They are pretty much in their we can say developmental process. Not much has been seen towards this. Now why do we say capacitive sensing can be used as an option for conventional methods? Firstly, capacitive sensors can be totally non-invasive. Fine. We can put the capacitive sensors on the bionic hand itself, and the skin will work as the second electrode, and there will still be capacitance present, and the air between the two can work as an air gap dielectric, and we can use capacitive sensing perfectly fine. Fine. Also, one more attractive thing is it does not depend on the muscle fatigue. Even if the muscle is fatigued, you can still use it because capacitance is still there. Fine. Another thing, the power consumption is very low because we know capacitive sensors do not require very high level of excitations. Because of this, power consumption is low, number one, and number two, they are less interfered with by EMI these noises. So these are very attractive features that we can use. Fine. Now this is the workflow of the bionic hand that we are currently working on. What we have done, first we have developed the signal conditioning circuit. Why we are starting from this, that will come to on the next slide. The converting of impedance signal into a voltage signal or a current signal. After that, we have given it to an ADC to digitize it. Fine. We have interfaced this digitized signal to a microcontroller, so we can control the motor or the prosthetic drive that controls gesture control and all these things. What we have done till now, we have interfaced the digital signal to the microcontroller. This is the part we have completed up till now, and next we'll be developing the motor drive. And in the picture, I guess it's not working. The picture in the middle where you see the hand and all, this is the placement of electrodes, how the battery will be placed, and how the entire system will look up. Okay, we are already done to the microcontroller part. At this time, we are working on the motor drive. So how we can control the entire bionic hand, fine? So now, why do we need such a complex circuit? First, we'll look into that, fine? In figure 7, if you see carefully, capacitive sensor is not straightforward as it looks, fine? If you see, there is a term C0 at the top in figure 7. It represents the offset base capacitance, and this offset base capacitance is always very large as compared to the incremental base capacitance, that is delta C, fine? Because of this, what happens, the change that we get at the output is very poor, fine? So the sensor does not remain with a high resolution anymore. The resolution of the sensor decreases very much, fine? So we want this base capacitance to be as small as possible, but unfortunately that is not the case, fine? Because you develop a sensor or you buy an industrial sensor, it will have some base offset capacitance. The another issue which is very important is Rx. Every capacitive sensor has a parasitic resistive component in parallel. If it remained constant, no issues, we would have left as it is, but it changes. It might change with the measurement itself, it might change due to temperature as well. Otherwise, capacitive sensors are very non-sensitive to temperature variations, but due to this Rx, it becomes temperature variant. So we have to take part of this Rx as well. Another thing that you see are CP1 and CP2. These are more parasitics that are involved. So what we have done basically, going through the circuit, we have excited the sensor. In figure 6 you can see, we have excited the sensor using a sinusoidal oscillation, fine? At the output of OA1, basically OA1 simply works as an impedance to voltage converter, fine? If you see OA1 output, there are two terms, there is a real part and there is an imaginary part, fine? And when there is J involved, you translate it into time domain and it simply means shifting by 90 degrees. Somewhat kind of phase shifts by 90 degrees, nothing else. So what we have done, we have phase shifted the excitation signal by the same 90 degrees using a quadrature phase shifter and given to a multiplier. Basically, what is this part? This part is what we call as phase sensitive detection, fine? At the output, basically what happens here, the capacitive part of the sensor will be brought very close to DC or to a very small frequency, and the resistive part of the sensor, this will be taken to almost 2 omega or 3 omega maybe. Basically what we want to say is to a very high frequency, and then after that what we do, we use a low pass filter. Using a low pass filter, simply the high frequency components get filtered out and the frequency component which are at very low frequency, these remain within the circuit or are present at the output of the low pass filter. Now, so basically what we have done up till now, we have taken care of Rx, but C0 still remains. So what we do, we use an integrator in the feedback loop. Using an integrator in the feedback loop, what we do, using the LPF output, we charge the integrator Ci, fine? Now using Ci, we give it to another multiplier, and we excite the signal using the same frequency, V in I of t, as you can see. Now this Cs, this plays a very important role over here, fine? Even if Cs is not equivalent to C0, we might say that there is no offset cancellation, but depending on the output of the low pass filter, the value of integrator, that is Vc, it changes accordingly. Because of that, what happens, the current passing through Cs, capacitor Cs, it becomes equivalent to the current passing through C0, and because of that, what happens, OA1 works as a subtractor circuit for these two, and hence we obtain offset cancellation as well. Fine. So what we have done, we have obtained offset cancellation, we have obtained a parasitic resistance cancellation. There is only one thing that remains, that is the drift compensation. Let us say we have a sensor to fabricated a sensor today. Post 10 days it won't show the same readings. Why? Because there is always drift. Sensors are always drifting, may it be long term drift, may it be short term drift. Then it will cause again a problem. But since we do not require any matching between capacitor Cs and capacitor C naught, therefore this drift will always be automatically tuned. So what we want to say is, this circuit does not need any kind of external calibration. It is self-calibrated, it is self-tuned. Once you calibrate it, the integrator will always, what we can say, charge up to a higher level or to a lower level to compensate the drift as well, or the C naught value as well. Fine. Now another thing, the value of CP2 is already diminished. If you see carefully at OA1, both of the points of CP2 are at ground potential. When you connect it, it comes at ground potential and hence it is eliminated. Fine. Also, from figure 4, you can see when the value of Cx, that is the incremental resistance, on the bottom right corner, the value of Cx, when it is changing, the voltage Vc is changing proportionally. It is linear, it is proportional. So again an added advantage. This can be also used as output for measuring Cx, as well as the point at the output of the low pass filter. Fine. So this is the output waveform. Please leave the transient part, we have showed it as well. Now so if you see, let us at this point over here, what is happening, as soon as a capacitive touch or some change in capacitance is monitored, the integrator, which is in the red waveform, instantly it starts charging in the opposite direction. Thank you so much. Here, the LPF output means a capacitive touch or a capacitance change has been observed, and in correspondence what happens, the integrator output starts charging in the opposite direction almost instantaneously. Fine. And after this it maintains a certain level of voltage, let us say 1 volt. But if you see, the output of the LPF is stuck at 0. Fine. It is stuck at 0. And again, when a touch in the opposite direction comes, touch in the opposite direction means, let us say in this case, the sinusoidal part was in its positive polarity and here it is in its negative polarity. That is the only reason it's coming on the other side. The integrator again charges in the opposite direction, maintains some voltage to make to auto zero the circuit. Fine. Hence we have used a DC servo loop or an auto-nulling circuit to compensate for the drift and parasitic of the capacitive sensor. So these are the conclusions and what we have obtained so far. Okay. Thank you.